Welcome back. In this video we are going to discuss about the upsampling and its time frequency index mapping. Okay, so far we had discussed about the downsampling, we discussed about the magic formula, right, and we discussed about the effect of this frequency, effect of the downsampling on the spectrum of the signal. And so in this video now we are going to discuss about the upsampling. So we'll start off with the time frequency index map, and then we will look into the spectrum of the upsample signal, and we'll see some of the numerical examples. Okay, so to start off, we'll do the similar kind of an analogy that we had used to derive the relationship for the downsampling. That is, if I have the signal which is originally sampled at 1x already, and if I am going to upsample it at a certain rate, then what happens to the index? Okay, so what I'll do is I'll follow the same style which we had used for the downsampling. Okay, so I will consider I'll divide this thing into two sections. Let's call this thing as okay, let's call this one as the originally sampled. It is originally sampled. Okay, discrete signal, okay, or discrete sequence I would say, and let's call it as 1x, right? And on this side, let's change the color. Okay, this one, let's call this one as the upsampled. Okay, this is our upsampled discrete sequence. Okay, so what we are doing here is we already have the sequence at 1x, and then I'm going to upsample it by the factor of 2x, let's say, for example. Okay, so let's call this as 2x. Okay, and let us denote the sampling frequency of this guy as f dash s, okay, and which is equal to 2 times fs, where fs, okay, let's go back to the original color, something like this. Okay, so let's call this thing as 2 times, okay, let's call this as 2 times fs, where fs is the original sample frequency. So let's close this. Okay, so originally we have the original sample frequency fs, so this we call this as fs. So let's do the time frequency plot similarly. So we have the index, we call this as the running time t, okay, and let's call the second scale as running frequency f. Okay, these are the analog time and analog frequency, and we are going to divide this into n number of points. Okay, so let's say it's 1, 2, 3 and 4. Okay, so let's call this as n, that I have actually sampled at certain rate using the sampling frequency fs, and I have got n number of sample points. Okay, and in the frequency domain also I'm going to see the same number of points, right? So this is n, but on this side it's going to be slightly different. Okay, so on this side what we'll do is okay, so we'll have a similar scalings for analog time and the analog frequency f. Okay, but the number of points that I'm going to take in the upsample signal is 2 times x, okay, twice the sampling frequency. So what it means is that I'm going to have twice the number of samples what I used to have in my originally sampled signal. So so here I have, let's say 1, 2, 3, 4, 5. So basically I should be having here around 10 samples. Okay, so just rough 5, 6, 7, 8, 9 and 10, something like this. And the same thing I'm going to have here in the frequency domain as well. Okay, so here the number of points that I have is now 2 times of n. Okay, we can call it as n dash. Okay, we can call it as n dash. N dash is equal to 2 times n, right? And we already know that the sampling frequency f dash s is twice the sampling originally sampled frequency, correct? And what about the running time and running frequency index? That would remain the same, right? So let's call this guy as n. So this is n and this is k, right? This is my running frequency index and this is my running time index, and both of them, they are going to vary between 0 to less than equivalent to n, less than equivalent to n minus 1, and this guy also 0 less than equal to k, less than equivalent to n minus 1. But here we will see a slight difference. So here what you're going to see is the running time index n that we have is going to vary between 0 to 0 less than equal to n less than equal to 2 times n minus 1, right? Or we can call it as n dash, or you can call it as n dash minus 1. They're both one and the same. And the running frequency index k is going to vary from 0 less than equivalent to k less than equivalent to n dash. Let's keep it as n dash only. So okay, n dash, and just for the clarification we can put this to 2 times n minus 1 here. Right, so now we have two sections. One is going to derive the time frequency mapping for the originally one example signal, and one is going to derive the time frequency map of upsample signal. Okay, so now here what happens, let's go back to our original derivation. Okay, so we had this magic formula, right? And f times t is k times n by capital N, right? We had this magic formula that f times t is equivalent to k times n divided by capital N, right? So this was a derivation that we had from originally sampled signals. So we'll do the derivation here once again so that we are more thorough. So now f times t, right? Now this product, how am I going to represent this in the discrete domain? So we had already seen that, well, f is equivalent to what? F is equal to delta f times k, right? And delta f is nothing else but this. This is my delta f. This is the delta f. And what is my running time t, analog time t? It is equivalent to n times delta t, correct? It is n times delta t. And what is delta t? Delta t is the sampling time. This is what we call it, a sampling time, right? And we had seen the further simplification. So if you further simplify this, the delta f is this spacing, and it is nothing else but if you see this point, final point is f is equivalent to fs, right? So can I say that, well, it is equal to fs divided by n number of points, right? So this is my sampling frequency divided by n number of points, right? That is my delta f times k, and then I have n times delta t. Okay, and we had seen before that delta t and fs are inversely proportional to each other. They are inversely related to each other. There is direct 11-to-1 mapping, and so delta f and delta t cancels out, and what we are left with is equal to k times n by capital N. Okay, so this was the relationship that we had derived from originally one example signal. Now let us consider this guy. Okay, so this guy is already in discrete domain, but now I'm increasing the sampling frequency. So what happens to the indexing? That's what my main objective is to find out, right? So we'll follow the same derivation, right? So f times t, how we are going to derive the discrete indices from this. So okay, so let's call this guy as f dash s. Okay, delta f dash, and let's call this distance as delta t dash, right? So now we know, well, f is equivalent to nothing else but k times what? Delta f dash, right? And what is t? T is n times delta t dash. Okay, and following the same derivation, so we can say that, well, delta f is nothing else but, now here I have f is equal to f dash s, which is equal to 2 times of fs. Okay, so we'll just replace here by f dash of s, which is basically a different sampling frequency at 2 times x, right? And f dash s divided by 2 times n. Now this point is important, 2 times n, because I have 2n number of samples, right? I have 2 times n number of samples. So here I'm going to have 2 times n rather than n, and here this will remain as it is, so n times delta t dash. And following the same understanding that f dash s and delta t dash, they are going to cancel out. So what is left is, it is k times n by 2 times n. Okay, so now if you compare these two guys, can you find out what is the similarity between the two and what is the difference between the two? So the denominator term has got increased by the factor of 2, and this factor of 2 is nothing else but my upsampling factor. Okay, so this factor of 2, this guy is nothing else by, it is my upsampling factor. Okay, it is my upsampling factor. Okay, so how do I generalize this? So we can say that, well, if I have a signal, if the signal is sampled, if a discrete sequence, okay, is sampled, let's call it as upsampled, right? Because we are deriving the upsample relationship, is upsampled at upsampling rate, let's say upsampling rate u, right? Then in that case, the time frequency relationship is going to map as f times t is equivalent to k times n divided by 2n. Okay, so this is the final derivation that we have. So the way you are going to do the mapping is going to look like this. Okay, but I would say that it would be also more realistic, or it would be more intuitive to write, because you can represent the analog domain quantities with any notations, right? So this 2 times n could be equivalent to some other n, or n dash something, but this 2 times n is supposed to be related to the originally sampled frequency. So okay, what I'm trying to say is that kn by n, okay, at 1x is related to kn by 2 times n if I have, or u times n. Okay, let's call this as u, and this is also u, right? This is any random upsampling factor that we can take and as an integer, where u is an integer. U is an integer, and we'll come to that why u needs to be an integer, right? So this is what the final relationship that we have. K times n by capital N is equivalent to k times n divided by u times n. Okay, so in the next video we'll discuss about the spectrum and how the spectrum looks like for an upsampled signal, and we'll also do some numerical analysis. So I will see you in the next video, and I hope you have enjoyed this.